right, today we're going to introduce the topics of thermodynamics that address the problems of what is a spontaneous reaction. I mean, what makes a reaction go when you don't have to do anything. You just put the reactants together and it's off to the races. And in order to do that, we need to introduce a couple of new topics. So let me share that PowerPoint. Yeah, let's see here. There we go. Okay. And make a slideshow out of it. There. Yeah, I'll rearrange some things for my own benefit. Okay. So this in your textbook is chapter 17. This will be the only exam material on exam 6. And it'll be the next to the last topic. The last topic will be electrochemistry. But we're just going to cover chapter 17 today. Here we go. All right, just a refresher. We've already covered topics in kinetics, which discuss the speed of a reaction. And you're all familiar with this diagram where you have starting off with reactants and the reaction progresses toward products, and the energy level of the reactants might be here. The energy level of the products might be here. And this part of the reaction where you reach the activation energy, and then if you get enough energy, you can go down the other side, is addressed by kinetics. The before and after situation, the reactants and the products, is addressed by thermodynamics. And there's a major difference between the two approaches. The topic of kinetics is references path functions. In other words, the speed of the reaction does depend upon the path that the reaction takes. That's why mine's gone blank. Catalysts. That's why catalysts work. Catalysts provide a reaction with an alternate pathway. And that alternate pathway gets you there quicker. The thermodynamic topic just tells you whether a reaction will proceed at all under certain conditions, and speed is not an issue. In fact, there are some reactions that will proceed spontaneously. Well, I guess I'll have to define what that is, but they will run, but they might take a very long time. For instance, diamond thermodynamically, in an oxidizing atmosphere like the air we breathe, will spontaneously convert to carbon dioxide. It will oxidize. Since diamond is pure carbon, then it would react with oxygen and produce the end product. Thermodynamics says, oh yeah, it'll go spontaneously. No outside intervention required. The thing about it is, though, that reaction, while it's thermodynamically favorable, it'll take millions of years to happen. So that's just an illustration of the differences of kinetics and thermodynamics, and that you can't get all your answers from one. You need both. Okay, so this is just a summation of what I just said. Thermodynamics predicts the direction that a process will go spontaneously. Spontaneous just simply means no outside intervention required. Now, that doesn't mean that a reaction won't go the other direction. It won't go backwards. For instance, if this is the spontaneous direction from A to B, the reaction can go backwards. And we've already seen in our discussion of equilibrium that this will happen. The reverse reaction will happen at the same time as the forward reaction. But we also know how to express quantitatively that reaction balance with the law of mass action. But the spontaneous direction, as written, should be from A to B. That means non-spontaneous is from B to A. Now, you can drive a reaction backwards, or you can change the conditions that will also change the direction that a reaction goes spontaneously. If we change the temperature, for instance, depending on what type of reaction it is, it might reverse and go this direction spontaneously, then the other direction not spontaneously. Or you can couple it with another reaction. Couple it with a reaction that goes spontaneously more energetically than this one does, and it will provide the energy requirements for running the reaction backwards. We do that in our air conditioning systems every day, in your car, in your home. We drive the reaction in a non-spontaneous direction. Okay, so let's consider this hypothetical situation. You've got a telephone that's ringing and needs to be quiet. Let's say you have a situation where you've got a 4-liter bulb on one side connected to, through a valve, a 20-liter bulb on this side. So that's 20 liters. This is 4 liters. This side is a vacuum. There's nothing in it. On this side, we've got 2.4 moles of gas. Okay? And the temperature is 32 degrees. Constant. So no matter what the reaction does, we have constructed this experiment so that the temperature will be maintained at 32 degrees no matter what happens. So what are we going to do? Well, we're going to open the valve, of course. I mean, we're not just going to let it sit there. What happens when you open the valve? Intuitively, you know that the gas from this side is going to whoosh into that other side, and then they're going to balance so that the pressure throughout will be the same. All right, what's the driving force? Why does it go? Well, let's look at the various parameters that we can use to describe a reaction. Delta H is the enthalpy of the reaction. That is, it's the heat potential that is available from a reaction. And I'll prove this one later. Internal energy plus, that is, this value, delta E, plus pressure times a change in volume is equal to enthalpy. Internal energy is the total energy that's inside the system, whether it's kinetic or potential, it doesn't matter. That's the total energy. And then any change in pressure and volume, plus that internal energy, will describe enthalpy. Now, you remember, I hope, from first semester when we discussed thermochemistry, we sort of introduced concepts of thermodynamics there, but we didn't go into depth. We were only interested in the first law. When we describe Q, we're actually measuring heat flow into and out of a system. And in order to do that, you need a temperature change to occur, because heat won't flow between two connected objects that are at the same temperature. And then what we mean by work is a physical definition. W, work, equals a force applied through a distance. If you don't get a force applied through a distance, you don't have work. So that's why we need to, especially for gases, and it's easiest in chemistry to describe work in terms of gases, although it's not required. But the concept is easier to grasp. If you apply pressure in a cylinder that has a movable piston, all right, so you have gas in here under pressure, and if the pressure changes inside, but the pressure outside does not, it's constant pressure, then the piston will move, right, until the pressures are balanced. In that case, you've changed the volume. But since the diameter and the area of that cylinder is constant, then you have moved that piston through a distance. And the pressure is applying a force, actually a force per unit area, but the total force can be calculated. So force times distance gives you work. So if that piston moves, the gas has done work. In this case, if it moves up, it's doing work on the surroundings. If it moves down, say the pressure decreases, then the surroundings are doing work on the system. Okay, so now that those definitions, I've refreshed your memory. During this process, what happens to those values? Calculate these delta H, delta E, Q, and W for that process. Well, as it turns out, in order to transfer heat, you need a difference in temperature. But we just said the temperature is not changing, right? So you don't get any heat transfer. Consequently, you don't get any delta H transfer either. And you don't, and we're going to save E just a minute. W, has any work been done? The gas just moved, right? It didn't apply a force to anything. It just moved from here to there, right? No piston moved. We were not able to sense or evaluate any work being done. So all those values are zero, right? Constant temperature, delta H is zero. Delta E is zero. All right, energy. You can't get any energy transfer without a change in temperature. Work. No work was done. The gas was moving against zero pressure into an evacuated cylinder, evacuated bulb. Okay. We can also deduce delta E by another way. Remember, delta E is equal to heat transfer plus work. That's a change in internal energy. If you get a change in heat or a change in work or both, or you get one going one direction, one going the other, and the signs coincide and you calculate a value. Well, what did we just say? There's no work being done. There's no heat transfer. So you add them together and you still get zero. So all of these values for this process are zero. So how do you explain it? Right? In the past, we said a chemical reaction tends toward more stability. Right? So the exothermic reaction would tend to be preferred. In other words, you may have to put a little bit of energy into it to get it up to that hump and then over the other side. But once it's over the hump, and that's kinetics, right? So we're not talking about kinetics here. Once you get it to the other side, the energy of the products is lower than the energy of the reactants. That means more stability. That would be considered a driving force for the reaction. But there's not even that going on here. So how do we explain it? What is the driving force for this process? Something has to make it move, right? Otherwise, all that gas would stay over here. I had a cell physiology professor who used to describe it this way, and he used statistics. He said there's a very small statistical probability, I mean, vanishingly small, that all the air in this room will migrate to that corner and we'll suffocate. Now, statistically speaking, that's true. It could happen, but it's not very likely. And similarly, when we open that valve, you know, all that gas could stay right there and not move at all. But the probability is much greater for it to move. And our discussions from now on have to keep that statistical perspective in mind. What's the driving force? Well, we had to invent a new term. In fact, I didn't invent this term. This term, in fact, was invented by Rudolf Clausius in 1854. At the time, we were at the beginnings. Well, actually, we were in the middle of the Industrial Revolution. Now, you can get a more complete definition of Industrial Revolution in a history course. But to make a long story short, animal and human power was being replaced by machines. And we were able to extract energy from stored energy sources like wood and coal. And petroleum wasn't real big yet. Coal was the main thing. And the center of this industrial revolution was England. But other countries were getting involved, and Clausius was one of them. He was German. But the Carnots, the father and son, were also interested in what we call heat engines. In other words, extracting useful work from the heat, the energy that's stored in these fuels. The interesting thing was these, and we refer to steam engines. They were very popular. These steam engines were discovered to be only about 2% efficient. So the energy that was being released by the fuels, we're only getting about 2% out of it as work. And there were several scientists that were interested in why this was. You know, where's all that energy going? Why can't we increase the efficiency? Our heat engines now, the typical automobile engine will get maybe 30–35% efficiency. And we've got some experimental units that are up close to pushing 50% efficiency. Well, it was all the revolution in thermodynamics that allowed that increase in efficiency took place in the middle of the 19th century with Rudolf Clausius and others. Boltzmann was one, and we'll mention him a little later. But Clausius invented this term, entropy, and he gave it the symbol S, a large S, capital S. And that was his descriptive term for that loss of energy. The system was losing that energy. And others developed it further. and it came to be a term, actually a statistical term, reference to energy. All right, so let's give it a more complete definition here. All right, so let's look at it in terms of what we have just described. In this case, both the cylinders are the same size, obviously, but the concept is the same. So here we have our two cylinders, and the gas is confined in one side with a vacuum on the other side. So when you open the cylinder, open the valve, what has changed? The obvious change is that the molecules are more spread out now. They occupy more space. All right, that's the difference between the two images. The molecules now have more room. In other words, they can occupy more different places. That's what we call entropy. They have increased their entropy. And one way to look at it, although it's not the best mathematical way to look at the situation, but it's a conceptual aid, is the concept of disorder. You see that there's more disorder. In other words, when you pack gas closer together, they have to be more orderly because they're in smaller space. If you increase the space, then they can become more disordered. And that's one concept for describing entropy as a measure of disorder. So we have to consider entropy in terms of, just like we did with thermochemistry, where we have a description of the system and everything else is surroundings. Right, so you can get heat transfer across that boundary, or if we allow it, you can get mass transfer across that boundary. But in order to simplify the situation, we want to confine our discussion to system and surroundings in a more localized region. So we do this. And we say, now we are isolated. So system and surroundings are isolated from the rest of the universe. So when your textbook talks about universe, sometimes they mean the real universe with a capital U, everything. But sometimes when they say U with a small u, they mean this situation where we've isolated the surroundings and the system, and we can discuss them in detail. Okay, so unless I explicitly say the entire universe, then I mean this. And I'll actually reference what's going on in terms of total rather than universe. So I'll say total. I'll avoid using universe unless I actually mean the universe. Okay, so this measure of disorder is expressed as a change, right? It's like heat. You don't have really a way to express heat unless you get movement, which means delta, a change. You have to have a change to measure. Absolute values are almost impossible to obtain. So we say the delta S, the change in entropy. If it's positive, greater than 0, that means you've increased disorder. And of course, if it's negative, you decrease disorder. You've brought more order to the system or the surroundings, as the case may be. All right, while this concept is grossly oversimplified, the disorder concept, it still is useful. Okay, let's see, I want to keep myself on track here. Let's review our laws of thermodynamics. Okay, so the first law of thermodynamics we discussed that one in the first semester under the topic of thermochemistry. In other words, the total change in entropy for the universe is zero. That's the simplest way to put it. In other words, whenever you get a description of energy before and after, say in a chemical reaction, you don't add energy, you don't subtract energy, you might change its form, but you don't create energy, you don't destroy energy. Right, that's the first law. The second law of thermodynamics refers to entropy. And here again, I do mean the universe, the entire universe. All processes taken together in the universe, sum them up, and you always get an increase in entropy for the whole universe. Now, of course, if we isolate like this, you can get entropy going in negative directions as well. But for the whole universe, entropy always increases. That's the second law. We'll get to the third law later. It's not as important. Not to us anyway. It's important to people that spend their lives studying this stuff. Okay. A better way to describe entropy is in terms of how many possible arrangements of molecules are there when you open that valve. All right. Do the number of arrangements of molecules increase or decrease? The number of those arrangements has increased because you're giving the molecules more space, so they can be more different places. What we call these are microstates. And this is a statistical term. It doesn't mean that you change from solid to liquid to gas. That's state, the state of matter. But microstate refers to the number of possible arrangements of all the particles in the system. And a spontaneous movement always moves toward the highest probability of these microstates. So if you have, well, let's go to the next slide and we show example here. Let's keep it really simple. Let's say we have these two bulbs, and you have, statistically speaking, there's a probability that all of those four molecules will stay in one side when you open the valve, and they won't move. That's one microstate. Another microstate would be if all of them move to the other side and leave a vacuum on the other side that they just left behind. That would be another microstate. A different description. Now, this second possible arrangement would simply move one of the molecules over, one at a time. So A could be over here, B could be over here, C or D could be over there, and the other three are left behind in the other cylinder, the other bulb. So you have four possible arrangements there, where you have three on one side and one on the other. Okay. It's kind of like if you've ever had statistical course, they always start out with flipping a coin. You know, what's the probability of getting heads? Well, 50%. Well, this one has is more probable than the first arrangement, but not by much. Right? It's 4 times more probable than the first arrangement, and it's 4 times more probable than the last arrangement. Well, what if we move all 3 over and leave 1 behind? You have 4 possible states there, right? So it's 4 times as likely as these others. But what if we only move 2 over at a time? What could you have? Well, now you have A, B, and C, D, but you could have B, C, and AD. You could have AC and BD, or BD and AC, or AD and BC, or CD and AB. You have 6 possible states. This is the more probable because there are more possible microstates. So this probability expression is closer to the quantitative evaluation of entropy, right? We're moving from conceptual toward quantitative descriptions. And in order to do that, we have to discuss this in terms of statistics, right? So there's probably a better definition than I gave you. Each configuration is a microstate if it gives a unique arrangement of particles. All right, so let's see if we can develop an intuition about entropy. And we're going to fall back on the concept of disorder. Okay, so and in this case, we're only talking about positions of atoms or molecules. In this previous slide, we were looking at positions of different molecules, but you can also describe this, and in fact, the original description of entropy was in terms of energy, not particles. So what's happening to the energy, right? Well, you can visualize the movement of particles over here as, well, if this particle moved over here, it carried its energy with it. You look at it in those terms, and then it helps make sense of moving particles or moving the energy associated with them, right? So in this term, in this description, we're only concerned with position. How many possible positions do you have, microstates, of an element in its solid form, in its liquid form, in its gas form? Well, I think it should be fairly obvious that the most disorder you would experience for this element would be in terms of its gas. It has the highest entropy as a gas. So liquid would be less than that. But liquid would also be a bit more disordered than solid. Why? Because the solid atoms, in this case, are locked in their position. They don't have the opportunity to acquire more microstates as a liquid would. Liquid molecules or atoms can move past one another. Now, how did we get there? Well, to go from solid to liquid, we had to add energy. Right? So energy is involved here, even though we're only talking about position. And similarly, to go from liquid to gas, you have to add a lot of energy. Okay, so I hope that positional probability of these states favors gas, right? So if we're only talking about entropy and position, we would expect the spontaneous movement to be from solid to liquid to gas for position. Okay, there's another concept of entropy that I referred to earlier, energy entropy. It's not covered in your textbook. I searched the textbook and it's not there. But the authors of the textbook do reference the balance between positional and energy entropy in subsequent discussions. And I thought that was kind of strange, you know, if you're gonna say positional entropy versus energy entropy, you ought to at least define your terms, and they didn't do that. So that's what I'm trying to do here. I don't know if I'll succeed, but I'll give it a whack. So the total randomness of the system, or the total entropy, is a, well, actually the total and I'll put that back if I need it. The total is a summation of the change in entropy of the system plus the change in entropy of the surroundings. Okay. What we would expect is that for an exothermic process, that implies an increase in energy randomness for the surroundings. Right? So that would increase the amount of energy in the surroundings, which would increase the number of energy microstates for the surroundings. Right? So what happens to the system? Well, you would expect if you're transferring energy out to the surroundings, you would decrease energy for the system, and decreasing energy for the system would be a decrease in entropy for the system. Right? And if we're just looking at the system, we would expect that lower energy would be more stable. Right? Based on our previous concepts, you decrease the energy of the system, you would expect it to be more stable and be preferred. So what does that mean in terms of our previous slide? The preferred state would be a solid, correct? If energy is leaving, exothermic, then the solid would be preferred over the liquid or the gas. All right. For an endothermic process, you're increasing the randomness of the system at the expense of the surroundings. And in that case, that would be an endothermic process going this way. An endothermic process would decrease the energy randomness of the surroundings and increase the energy randomness for the system. That would be not preferred. So the preferred energy entropy is exothermic, which we would expect to describe a spontaneous process, whereas the endothermic would be non-spontaneous. Okay, in fact, the spontaneous reaction, or the process that is spontaneous, has a total delta S positive. If this is positive, no matter what happens over here, then the process is considered spontaneous. So it just depends on the change in these two. Right? So we have to assess both energy and position to completely describe these two terms. Here, we've just described the energy movement. Okay. So I'm on the wrong page, excuse me. All right. So let's see if we can intuitively describe delta S for each of these processes. Right? Remember, increasing delta S is positive by definition. Okay. How about the evaporation of alcohol? What would be the sign of delta S for the evaporation of alcohol? Well, it's going from a liquid to a gas. So we would expect the disorder for that gas to increase. Right? Oh, I forgot about this one. Let's get that one in there. So the evaporation of alcohol would be a positive delta S. We're increasing the entropy of the disorder of the alcohol molecules. It's important to recognize that delta S is not measured directly. In other words, you don't have a ruler or a device that you can hold up to a reaction or a process of any kind, and it will spit out the number delta S. Delta S is calculated. The original way to calculate it was in terms of statistics. This term right here, the W, is Ludwig Boltzmann's term for probability. Right? And he would take the natural log of that probability term and multiply it by a constant, aka Boltzmann's constant, and it would give him a term for entropy. But like so many of these equations, they're not very useful in that form. So other equations we're going to use in just a few minutes allow us to calculate delta S from other information that's given. And that took other scientists, several decades to tease out these other calculations. Before that, you had to be a theoretical physicist or a math genius to do this work. But it was a stepping stone. Okay, back to our problems. How about the freezing of water? By the way, it's not here, but while we're doing this, we're describing the delta S for each one of these, right? So we got a plus there, we got a minus for the second one, because freezing water is more orderly. You're going from a liquid to a solid. So delta S is more orderly. But let's also look at what's the delta H? What's the enthalpy of the reaction? I mean, is this exothermic or endothermic? Right? The evaporation of alcohol is endothermic. You have to add energy to the alcohol, which is our system, to make it evaporate. So this would be endothermic, a positive value, right? It's in terms of the system. Positive means you're adding energy to the system. Negative means exothermic, you're losing energy. So for freezing water, this would be exothermic, correct? It's more disorder, but it's losing energy. How about if we compress an ideal gas at constant temperature? Well, if you compress the gas, you're giving it fewer microstates available. It's in smaller space. So you're decreasing the entropy, right? What about delta H? Constant temperature? Delta H is 0 for that one. There's no movement of energy at all. Heating an ideal gas at constant pressure. So we're going to heat the gas at constant pressure. Remember, with constant pressure, Charles' law. If you heat a gas at constant pressure, then the volume will increase. Okay, so if you increase the volume as you add energy, right? You add energy, you increase the volume, you're giving those molecules more microstates. So you're increasing the entropy. Okay, another way to look at it, if you allow the pressure to increase as you add energy, you're also increasing the entropy because you're adding energy. Those molecules are acquiring more energy. They can get places faster, one place to the other. So more microstates are actually available in terms of energy. So increasing energy, adding energy to a system, all other factors being held constant, is also an increase in entropy. And dissolving sodium chloride in water. So sodium chloride solid, and that's what they mean here, dissolving the sodium chloride solid, is a regular crystalline structure. But when you put it in water, what happens? You get the ions, they're released. They're no longer in that structure. So aqueous solutions of solids always are an increase in entropy. What about this one? Well, you do have to add energy to break the bonds of sodium chloride, and you have to add energy to the water to make a whole. Remember, we talked about the solutions, how you make a solution. You break the bonds of the solute, and you break some bonds for the solvent, and then you reform the bonds when the solution is made. So the delta H for this one is unknown. It could be positive or negative because it's the summation, the endothermic breaking bonds of the solute, the endothermic breaking bonds of the solvent, and then the exothermic when you reform bonds between solvent and solute. So there, it could be positive or negative. We don't know. All right. So let's move, and this is the second law of thermodynamics. There's always an increase in the entropy of the universe in any spontaneous process. And I'm just going to beat this horse again. The universe is more manageable if we restrict its use. We isolate the system and the surroundings from everything else. Then it's easier to both visualize and discuss entropy. And this is just a restatement of the first law that I gave you earlier. Whereas the second law says entropy is always increasing, first law says the total energy in the universe, though, is constant. It doesn't change. So entropy is actually an expression of the distribution of energy and matter. And when we get to that, the formula that describes that quantitatively describes that process, then I'll hit that topic again. All right, so, well, I erased it, but this S for the universe, which is better described as total, is equal to the change in entropy for the system plus the change in entropy for the surroundings. So that's my choice. In fact, a delta out here would be better. Delta S total, delta S universe. That needs correction. So let me make myself a note here. Okay. So next, if the delta S total is positive, that means entropy is increasing. And here they mean total. Total entropy is increasing. That is spontaneous. Delta S for the total, if it's negative, that's non-spontaneous. But it is spontaneous in the other direction. Right? The opposite direction would be spontaneous. So just because you determine that delta S is negative is not bad news. because that also tells you that all you have to do is reverse the reaction and you get a spontaneous reaction. If delta S total is 0, that means you're in an equilibrium situation. There's no impulse now to move in either direction. So in our equilibrium equation, where we have defined our K value and we've done our calculation, if you have equilibrium concentrations of products and reactants, then there's no impulse to move one way or the other. Now, we know on a kinetic basis that there's activity going backwards and forth. Right? But thermodynamically speaking, the equilibrium is static. There's no impulse to move either direction and change the equilibrium position of the reaction. All right, so now we're going to, here's where the authors come back in. They step back in. All right, they've been absent for a while because they didn't describe energy randomness in detail. So here we have a process where we're going from liquid to solid. Got that a little bit too close. There we go. So let's say we're taking some substance, A, and we're going from liquid to solid. Yes. All right. Which direction involves an increase in energy randomness? In other words, which one process is endothermic? Are you adding energy, which would be an increase in energy randomness? Right? Well, you add energy to go this direction, right? So energy is added in this direction, okay? That increases energy randomness this direction. Right? Which direction involves an increase in energy randomness? Yeah. Well, wait a minute. Actually, we're talking about system surroundings. So which way increases the randomness of the surroundings? Right? It would be the exothermic process. Exothermic energy transfer implies stability for the system, right? So the energy randomness we're talking about here that transfer stabilizes the system, and that would favor, so energy randomness favors the solid, whereas positional randomness increases that direction. So this is positional. I don't want to be mistaken for pressure. That's positional randomness, where this is energy randomness. So one favors the solid and the other favors the liquid. Simply because when you lose energy, the system becomes more stable. So what's the balance between the two? That's the question. Let's see. Am I going to answer the question though? Yeah. Actually, the key to this whole balance is temperature. Under one condition, energy is favored. Under another condition, position is favored. And what I mean by condition, I mean at high temperature, one is favored, at low temperature, the other is favored. So what happens with high temperature and increasing temperature? Well, as temperature increases, positional randomness dominates. This movement is favored. Now, this is our sample system, but it doesn't have to be this transition. Now we're broadening our perspective. So at high temperature, you've got a movement of energy, for instance, right? What does that energy mean if the temperature is high? What does a change of temperature mean to this whole system surroundings? It means very little, right? At high temperature, it's kind of like I crossed paths with a billionaire on the street, and I say, you know, I'm feeling generous today. How would you like a buck? You know, the billionaire says, nah, I don't need it. So at high temperature, the exchange of energy is less important. So position becomes more important. Right? Positional randomness is favored at high temperature. Okay? So that's the first concept. What about at low temperature? Well, at low temperature, it's like if there's a panhandler on the street. You see them all over the town in warm weather, right? Any place, especially in front of down by the Beckley Crossing, right there at Eisenhower Drive and that stoplight at Beckley Crossing. You'll always see in the warm weather, you'll see a beggar down there with a sign that says, I'm hungry and I need money and stuff like that. They're professionals. Anyway, they would appreciate a buck more than the billionaire because they're at a lower level of income, right? So in that case, the transfer of energy, donating that buck, is more important than the position. So back to our chemical systems. At low temperature, energy randomness is favored. Right? So at low temperature, the transfer out that would give us the solid is favored. So now here's the big takeaway for this introduction of concepts, the balance concept. At what temperature do we find equality, balance, exact balance between energy and positional randomness? That occurs at the melting point, when you have both solid and liquid together. This is for our example, right? We can expand that to other things like boiling point. It worked the same way. At the temperature of boiling point, you have a balance. There's equilibrium between the positional randomness and energy randomness. Right? Hold on to that concept. It's going to be very useful. All right. So let's see if we can apply these, what we've learned, to these situations and describe them as either spontaneous, non-spontaneous, or we just don't know. What about a reaction that is exothermic but becomes more positionally random? Right? So A, little a, is exothermic. So we have a minus delta H, right? Exothermic. But we have more positional randomness. So we have an increase in positional randomness, right? What can we say about that? Both of these driving forces are favorable, right? No matter what the temperature is, right? At high temperature, of course, this would be favored. But at low temperature, this would be favored. But this one is exothermic and positionally random. So both are favored. Both are there at any temperature. So under these conditions, we're always spontaneous. How about this one? Exothermic, right? Negative delta H, but less positionally random. Right? Under what conditions would this one be spontaneous? If it's less, if this is dominant, then that occurs when the exchange of energy occurs a dominant at low temperature. So this one is, well, yeah, I'll just write it this way. Spontaneous, low temperature. Well, they're saying we can't tell. Well, that's true, right? But given the circumstances, we don't know, right? We can't tell. One piece of information we need is temperature. If it's low temperature, then it's spontaneous. The other way around. If this is positive delta H and positive delta S, right, then this is only spontaneous at high temperature. Okay? All right, what do we have left? Negative, positive, negative, 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 positive, positive. Oh, positive and negative. So if we have an endothermic process and energy positional randomness, positional randomness is decreasing, then this is never spontaneous. But what do we say about that? It's not spontaneous in one direction, but it is in the other direction. Same for this one. This would be spontaneous in the conditions that were given, but in the reverse direction, it'd be non-spontaneous. Okay, stop me anytime if you have questions, and I'll do my best to answer them. This is, as they say, a very heavy topic. So that just means that conditions for A and D are not affected by temperature, simply because you have this stability factor and that stability factor together, then any temperature will do. Now, the rate of the reaction, of course, that's a different topic. We're talking about kinetics there. Thermodynamically speaking, doesn't matter what the temperature is here. Doesn't matter what it is here either. It just won't go. All right. So the delta S Now we're going to focus on the entropy of the surroundings, because we're trying to develop quantitative expressions for these terms. And we're going to start with surroundings. Okay, there we go. So the delta S, the entropy of the surroundings, depends on the direction of the heat flow. Now, why is that? Why does it depend upon the direction of the heat flow? Because this is a, let's see, this is isolated, but this boundary is only closed. That boundary is closed. Remember what I said about you can have three types of boundaries. This was way back in thermochemistry. Three types of boundaries. You can have open. An open boundary is really not a boundary, right? It's like our southern border. You know, illegal aliens just coming across willy-nilly. You can transfer energy and matter across that boundary if it's open. If it's closed, the only thing that can cross the boundary is heat. So you can get heat going in either direction. That's our energy transfer, the direction of heat flow. So the delta S of the surroundings, now we can only reference it in terms of heat. Right? So if we add heat to the surroundings, the delta S is positive. It increases as you add heat to the surroundings. And consequently, the entropy of the system is going to decrease because we transferred some heat out. So delta S for the surroundings depends on the direction of the flow. If the flow is exothermic, where delta H, where this value is negative, if this is negative, then delta S surroundings is positive. All right? And vice versa. If heat flows the other direction, then the delta S for the surroundings is negative. Now, we're going to dovetail that together here with our previous discussion on temperature. The change in entropy also depends upon temperature. Remember, high temperature versus low temperature, which is more important, right? At high temperature, positional is more important. At low temperature, energy transfer or heat transfer is more important. So there's a relationship there. The delta S for the surroundings is related to the heat transfer. It's also related to the temperature, but it's related inversely to the temperature, right? Because the entropy is more greatly affected when you start at lower entropy. So if we start at lower entropy, that means low temperature, then the entropy change is larger. So there's an inverse relationship. In other words, delta S for the surroundings is proportional to the heat transfer, right? It increases directly as the heat transfer, but it's inversely proportional to the temperature. So that means the Q goes in the numerator, right? Because as this goes up, that has to go up. but it's inversely proportional to the temperature. So that's why we put the temperature down here, because as the temperature goes up, this goes down. Right? Now, we got one other problem, is the sign. If the heat transfer is negative, this is going to increase. It should increase. But if we leave the sign alone, it's going to decrease. So we have to fudge. Right? Delta Q divided by T. And actually, we're more interested in the potential for a heat transfer. So instead of Q, we're going to write delta H, the enthalpy. There we go. So that's our first quantitative, well, not our first. The delta S total is equal to the delta S for the system plus the delta S for the surroundings. That's quantitative, our first formula. But our second best formula is this one, the delta S for the surroundings. Now we can quantify what is the surroundings doing so that we can assess the total delta S. Then we get this formula. All right, so there we have, in words, right, the driving force is the magnitude of the entropy change, right here, equals the quantity of heat, delta H, divided by the temperature in Kelvin. So that the sign conventions are honored, we have to say, we have to use the negative. So here's the formula that we just came up with. And this heat flow occurs at constant pressure. And I'm going to prove that to you in just a minute, I think. Let me check my... where is it? Yes, next slide. This constant pressure is very important because the only time that delta H is equal to Q is under conditions of constant pressure. All right, so there's your first formula. The delta S of the surroundings equals minus delta H over temperature. And this is in joules, and this is in K. It has to be. There's no choice about that one. Okay. When is delta H equal to Q? All right, I just said it was when pressure is constant. Well, this is my proof. There are different values. Enthalpy is a potential. It's a state function. Doesn't matter how you got there. Whereas Q is a path function, and it's an actual measure of heat transfer with different paths available. The only time that these two are equal is when pressure is constant. All right, so here we go. This equation, you just have to accept it. I'm sorry. We don't have time to develop it in this class. The enthalpy of a reaction is equal to the internal energy plus any changes in pressure volume, pressure times volume. All right, that's true. So what do we know about delta E? Well, I showed you very early on, delta E is still equal to Q plus W work. So if we substitute Q plus W in there for delta E, we get this expression. Right? Now, what if the process takes place at constant pressure? Then we get this expression. We pull the P out of that change. So out here, P doesn't change. But in here, the volume can change. All right. One more step. We know also from thermochemistry that, and we derived, work is equal to the negative of pressure times a change in volume. So if we substitute minus P delta V in for W, we get this expression, minus P delta V plus P delta V. They cancel. So under those conditions, delta H is equal to Q. Now that's important because you can't actually measure delta H. You can calculate it, but you calculate it with values that were determined for you, right? So somebody had to do it. And Q is an actual measure of heat transfer. In other words, temperature change. That's why in thermochemistry, we're talking about, when we set up our calorimeter, we're quantifying it in terms of actual temperature change and heat transfer. Delta H is not part of the discussion there. It only becomes part of the discussion if the pressure is constant. Now, if the reaction takes place in a liquid or a solid form, and there are no gases involved, then you can assume that pressure is constant, right? It's 1 atmosphere pressure. But if you have a gas reaction, then you have to take great pains to maintain the pressure during the reaction process. All right, so there's my proof. Okay, now let's go back to that original formula where we had delta S total, that's my total, their universe. And spontaneous means delta S total is positive. Non-spontaneous is negative. So you add the delta S of the system together with the delta S for the surroundings, you get the total. And if it's positive, you have spontaneous reaction. So if we determine that the delta S is positive for both system and surroundings, that's obvious. It's spontaneous, no matter what. If, however, we find that the delta S for the system and the surroundings change is negative, then the delta S for the universe or the total is negative, and no reaction will occur, except in the opposite direction. Okay, what about the other? Well, what if the system is positive and the surroundings are negative? Only if the system has a larger delta S change than the surroundings. Right? In that situation, then yes, it will be spontaneous. Or if delta S surroundings are larger than the magnitude of delta S under conditions where delta S is negative. Right? So in those cases, the positive one has to be bigger than the negative one to give you a spontaneous reaction. That's the moral of this story. All right. So along comes an American, Josiah Gibbs. Gibbs was a gifted mathematician, but he was also interested in physical chemistry. So he applied his substantial math skills to solving this problem, the problems that were developing surrounding the concepts of spontaneous reactions. He was particularly interested in how much of the energy of a reaction or a process is available to do useful work. Right? So now we're getting back to those heat engines. How much of that energy that's released from the fuel is theoretically available to do work, right? Recognizing that probably all that energy will not be recovered, but he wanted to know what's the theoretical limit. And what he determined was this value, this amount of energy, which is in joules, available to do useful work, depends upon two factors. What's the enthalpy of the process? What is the theoretical maximum amount of energy available in this reaction? Subtract from that the amount of energy that is lost to entropy. So now we're going back all the way to, well, shoot, my mind's gone blank again. It was before, I'll think of it in just a second. Unless you've got it in your notes. I don't want to have to scroll all the way back to the first slides. Oh well, I'm wasting airtime here. Anyway, it's on the tip of my tongue. Shoot, I hate it when that happens. So let's get back to the topic. This calculation can be performed, and this is Gibbs free energy equation, and that we call it Gibbs free energy because this is the amount of energy, the free energy available to do work. Now there are other expressions that can be used, but this is the most popular one. And since we're limited on time and expertise of your instructor, we're going to stick with Gibbs. So you subtract the amount of energy that is lost to entropy. Now, why do we have to multiply it by T? Well, remember, right? That value, there's T embedded in it. So if you multiply by T, then you get rid of the temperature factor. And now each one of these terms is in energy units, right? You can't subtract apples and oranges, right? So you got to convert this apple into an orange so that you can subtract it from this orange and get that orange. All right, now whenever we have no subscripts, we're always, from now on, we're always referencing the system. So this is in terms of the system. So this delta S is actually not that delta S, but all delta S's have temperature built into them. Right? They're heat units, joules per K, always. So what if we divide this whole equation through by T? We're going to do some mathematical sleight of hand here. If you divide the whole thing through by T, what do you get? Well, this T cancels. And now you got T as a term in this one and that one. But we also want to convert this one to a positive, right? So let's divide by negative T. So if you divide by negative T, if you divide by negative T, then you get negative delta G over T equals negative enthalpy divided by T plus delta S for the system. Okay, and this is just a reminder, delta S for the surroundings is equal to negative delta H divided by T. Okay, notice delta H divided by T negative is this term right here. So we can substitute delta S for the surroundings in that equation. Now we've got this value equal to surroundings plus system, and that's equal to total, isn't it? Yeah, it is. All right. So let's just pull these two terms out, right? We don't need both of them. Delta S total is all we need to keep. So now delta S total is equal to negative delta G divided by T. So the total entropy change for our process is equal to negative delta G divided by T. All right, what does that tell you about, well, I mean, what does that equation tell you? It tells you that if delta S total must be positive, so now we're going to change this. This is now total, and this is delta G for Gibbs free energy. If this has to be positive to be spontaneous, what does delta G have to be? Delta G has to be negative, right? Because a negative times a negative is a positive. So whenever delta G is negative, that means a positive delta S. Now the magnitude of the value is dependent upon temperature, inversely proportional to temperature. Right? So temperature is still a factor, but we can say that if delta G is negative, then it is spontaneous to some degree. Okay. So let's see if we can explain this one. Right. Okay. A liquid is vaporized at its boiling point. So here's one of those tricky word problems. A liquid is vaporized, right? So we have the liquid going to the gas at what temperature? At the boiling point. Okay, so what's W? Well, if you consider that your system is coupled some way to extract that movement, then you can say that work is negative. In other words, if we say and you got a liquid here going to gas, right, then that piston is going to move. We should have specified also its constant pressure. I need to do that too. Let me make that note for myself. Constant pressure. Okay. Then the convention is the system inside here is doing work on its surroundings. So W is negative. Okay. How about heat transfer? You have to add heat to vaporize a liquid to a gas. Right? Heat is required to break those bonds. How about delta H? Well, here again, I need to say constant pressure. If we got constant pressure, then Q is equal to delta H. Right? So it's positive also. How about the delta S for the system? What's happening to the system? You're becoming more disordered in the system because you're going from a liquid to a gas. Right? So that just stands to reason. Delta S for the system is increasing. How about surroundings? Well, surroundings, you have to extract energy from the surroundings, so that value is negative. Okay? Surroundings become more ordered, energy-wise. How about delta G? Well, what is delta G? I erased it. Delta G is reference to system, right? So if the system is, no, total, excuse me. The total is 0, correct? Remember what we said. The equilibrium position for a reaction is the place where there's no spontaneous drive. In other words, the delta S total is 0 at the boiling point or at the melting point. So delta G here has to be 0. That's where this key comes in, this boiling point. At the boiling point, you're at equilibrium. That's why, remember in discussions of thermochemistry, I described, let's see, where is it? I described phase changes, where you have progress of the phase change here, and you have temperature there. So if you start off at a solid, and you can heat the solid up a little bit, but then once you get to the melting point, temperature doesn't change, right? There's no change in temperature, and that corresponds to our discussion now that there's no free energy, right? There's no spontaneity. And then this is where you have solid and liquid. And then when you get all liquid, you increase the temperature again until you get liquid. And then you get to liquid gas. And then once you're all gas, then you increase the temperature some more. Only in these places right here, and here, and here, do you have a delta S change or a delta G change. Otherwise, you're at equilibrium right here and here. Okay? Also, in this case, delta G being equal to 0, like that, then if we say that delta G is equal to 0, of course, then delta H is equal to T times delta S, right here. Okay? So at equilibrium, we can set these two terms equal to one another. And remember, if there's no subscripts, we're talking about the system. Right? So the temperature, delta H for the system, delta S for the system, temperature of the system. Okay, let's use that information and see if we can answer this question. Solve this problem. What do we have? The value of delta H vaporization, right? That's boiling of the liquid. Vaporization of a substance is 45.7 kilojoules per mole. 45.7 kilojoules per mole. And its normal boiling point put that little 0 there, that means normal. What does that mean? Under conditions of standard temperature and pressure. Its boiling point, its normal boiling point, 1 atmosphere pressure, is 72.5 degrees. So there's not standard temperature, there's standard pressure. 72.5 degrees C. Okay? Calculate delta S, system, surroundings, and delta G for the vaporization of 1 mole of this substance at 72.5 degrees, at the boiling point. Right? We're at that boiling point. So what does that mean about delta G? That means delta G is 0, right? And it also means that delta S total is 0, right? So under those conditions, the delta S for the surroundings equals what? Well, the delta S for the surroundings is equal to minus delta H divided by T. Right? And that's what we've done here. We say minus this value, and remember, you got to have the same units. And delta S is always reported in the literature or in reference manuals as joules per K. Whereas many of the delta H calculations or reported data are in kilojoules. So that's the important stumbling block there. You got to get those units together. So that's why 45.7 times 3, 10 to the third, joules, right? We just take this K out and put it down here as 1,000. That's why I wrote it that way. And then you need to convert Celsius to K, divide that into this value, and now we get minus 132 joule per K mole. Right? So if this one is equal to minus 132 joules per K mole, and you're at equilibrium, then what's the system? Well, if delta S total is 0, this is also equal to delta S total. And you have to add these two together to get the total. Then if one of them is negative, the other one has to be the positive in the same magnitude to be 0. So this one is going to be positive 132. Oops, I almost made a mistake there. Joules per K mole. Okay. All right. Okay, I got a video coming up. This is Professor Dave. We've seen him before. And this video discusses entropy, but it also pulls some ancient concepts together and sort of ties them all together in one big basket. So be patient for about 8 minutes and let Professor Dave explain it perhaps in a different way than I would. And sometimes that clicks better when you hear it explained by somebody else. So here we go.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about science stuff, Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around. Entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T. So entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale, But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right, that was Professor Dave. I'll point out a couple of things that he mentioned. He was using the juxtaposition between energetically favorable versus entropically favorable. And I took that to mean that entropically favorable was more closely akin to the positional concept that we introduced earlier. And energetically was referencing the energy entropy. Now, I could be wrong there, but that's the way I rationalize it anyway. Another thing is, when he talked about the third law of thermodynamics, the one where the entropy of a perfect crystal at 0K is 0. The entropy of that system is 0. Gives us a reference point for all other entropy changes, which means that every delta S listed in every reference manual for any change is always positive. It's like Kelvin temperature. Kelvin temperature is always positive. Delta S is the standard delta S for any process is always positive. And it's always non-zero also. Remember when we were doing enthalpy calculations, delta H's for reactions, and we were interested in the total for the reaction. The total for the reaction, we had to find a 0 point, right? Because you had the enthalpies for the products minus the enthalpy for the reactants would give you the total. Well, anything that was elemental in its standard state, like O2 gas, that had a standard enthalpy of 0. Right? It's not the case for delta S. All delta S's are positive non-zeros for every reactant and every product. And we'll look at those in just a minute. We'll do an example. Okay, so let's look at these conditions. And this table is taken straight out of your book, 17.5. We're going to use Gibbs free energy equation to determine if a reaction under these different case conditions is spontaneous, non-spontaneous, or we don't know. Or we have to, we need some more information. So if delta S is positive and delta H is negative, what does that mean? Delta H is negative. If this is positive, then the term is negative. Both are negative. Delta G is negative. So it doesn't matter what the temperature is, it's always spontaneous at every temperature. Okay. What about, let's go to the last one. What if delta S is negative, right? The entropy is decreasing. and the delta H is positive, in other words, endothermic, then applying the sign and adding them together gives you a negative value. Let's see, excuse me. Right, if delta S is negative, that gives you a positive value here. And if delta H is positive, oh, okay. I had a momentary brain fart. If delta H is positive, delta S is negative, which makes this term positive, and both together are positive. Delta G is positive. This process is non-spontaneous at every temperature. It doesn't matter what the temperature is. Then you have in between. If delta S is positive and delta H is positive, then the only time you can have a delta G negative is when temperature is very high, which makes this term large enough to exceed the positive delta H. Okay? Then it would be spontaneous. If, on the other hand, delta S is negative and delta H is negative, then this term is going to be positive. So you want low temperature so that this positive is very small and the delta H is still negative, which gives you a negative delta G and a spontaneous reaction. So under those conditions, it's only spontaneous at low temperature, where exothermic reactions are dominant. All right. So let's go to calculating okay, we're going to do sort of an example here. We have an A2 gas reacts with a B2 gas that gives you 2 ABs. Right. So I take that as a diatomic gas plus another diatomic gas forms 2 of this binary gas. This is constant temperature and pressure. Okay, that's important. Temperature doesn't change, pressure doesn't change. And the bond energy of AB is much greater than that of either reactants. So what does that mean? If the bond energy is lower here than the total energy over here, then this reaction is exothermic. It goes like this. Products down here, reactants there. So it's going to give up energy. So delta H is negative. I'll talk about that equation in just a minute. Well, no, this is an equation we know already, right? We've done this one. Delta H for this reaction is energy of the reactants minus energy of the products. Yes, minus energy of the products is delta H. So these are the bonds that are broken. If you go through and measure every bond and add them up and then subtract the energy that you get back, all these values are positive, right? So that's why you need the negative sign and you need this order in the way it is. Once you find out delta H from this calculation, based upon what we know here, then delta H should be negative as an exothermic reaction. Okay? So what do we know about delta S for the surroundings? Well, if it's exothermic, delta S for the surroundings should increase. because we're transferring energy to the surroundings, right? And delta H for the system should be opposite sign, because where's the energy coming from? Well, it's coming from the system, transferred to the surroundings. Well, it's saying that we can't tell for sure, but I'm willing to bet that it's on the negative side. We're going to say it's 0 for now. Let's see. Do we need to say 0? Yeah, well, if we're at constant temperature and pressure, that's probably true. So now if we're going to say that surroundings is positive, then the total is positive. So that means this process should be non-spontaneous. Okay. Professor Day gave you this one already, third law of thermodynamics. So that means a substance, the entropy of a substance always increases with temperature. If it starts at 0, there's only one way to go is up. So under standard conditions, right, that little 0, the entropy for the reaction is the entropy for the products minus the entropy for the reactants. That's just like our enthalpy calculations, only now we substitute S in there. The same type of calculation. Okay, so how about the delta S, the standard delta S for this reaction? Right. Notice we have values for everything, even the elements under standard conditions. Right. So if we're going to take these, we're going to take these total and then subtract these total, what would it be? Rudolf Clausius. It just popped into my head. Introduced the term entropy. And he was concerned with what's happening to that lost energy. Okay, back to the topic. So if we have 2 sodiums, sodium hydroxide, that's 2 times 50, right, equals 100. And this is in joules per K. Why don't we have moles? Because this is moles. And this is joules per K moles. Moles cancel. Okay. We have hydrogen, which is 131, but there's only 1 mole. Yeah, that's messy. Okay, so now we take these 2 and we subtract 2 sodiums, 51, 2 times 51, 2 times 51 equals 102. And then water, 2 times 70 is equal to 140. So we subtract those 2 from these 2. And we get minus 11 joules per K. Right? So under standard conditions, the entropy for this reaction is negative. And that's the system. This is the system. So we can't say whether it's spontaneous or not. Remember, if we don't put a subscript here, it's the system. So the system entropy has gone down. It's more ordered. So the only way we can get a spontaneous reaction is if there was enough entropy produced in the surroundings to offset that. So the surroundings would have to be plus 11 or more. It has to be more than plus 11 to be spontaneous. We can also do calculations for Gibbs free energy, right? And those standard Gibbs free energy values are available in reference literature. And you've got two ways to calculate it. You can do the standard, and we still have this little zero in here. Why are we doing that? Because these values can change depending on the conditions, right? This is under standard conditions, temperature and pressure, and concentration for that matter. So delta G for the reaction is the product delta G minus the reactant delta G. Or if we happen to know what these terms are here and here, we can calculate it that way also. Or if you know delta G and you know this one, then you can calculate delta H. It's like any equation. One unknown, you can solve for it. Okay. So now we're going to try a little intuition. See if we can predict the signs for a stable diatomic molecule spontaneously forms its atoms. So we have this diatomic molecule. It doesn't say whether it's a gas or not. Spontaneously forms two X's. All right. What is required here in terms of energy? In order to break that bond, you have to add energy, right? So delta H must be positive. Excuse me. You have to break the bonds. So delta H oh, I got it backwards. No wonder it didn't make sense. Spontaneously forms from its atoms. There. Now it makes sense. When these two atoms come together to form a bond, they release energy. They're more stable, right? So delta H is exothermic. This is an exothermic process. How about delta S? Well, there's the delta H here because the molecules are at lower energy than the separate atoms. Okay, that's true. Delta S, we can look at it in terms of positional entropy. You're going from 2 moles of this to 1 mole of that, right? You're decreasing number of particles in the same space. So the entropy is for the system is decreasing also. And then delta G, since the process is spontaneous, we don't even have to do a calculation or know the temperature. It says it's spontaneous, so delta G has to be negative. All right, let's see. Okay, we still got time. All right, next. Suppose we have this reaction at equilibrium. Let me put that up here. Phosphorus trichloride, gas, plus chlorine, gas, at equilibrium with PCl5, gas. And the delta G is given. Delta G 0, standard conditions, is equal to minus 92.50, minus 92.50 kilojoules. So what does that mean? Well, the delta G, of course, says under standard conditions, this is a spontaneous reaction. But this system is now at equilibrium. So what does that mean for the actual G? The actual delta G is equal to 0. And this is 25 degrees, which is standard temperature. So under these conditions, we're interested in what's going to happen to the ratio of this one to that one. What about this ratio right here? There. We want to know, is that going to go up or go down if the temperature is increased? All right, so we've got our Gibbs free energy equation. Of course, that's natural because we have this right here, right? So we might as well use it. All right. What's happening to delta S in terms of this equation? Delta G equals delta H minus T delta S. Okay. So what's happening to the delta S here? We're going from 1, 2, down to 1. We're going from 2 moles to 1. This term is negative, right? We're decreasing the number of particles in the same space. We know what the temperature is, right? 25 or 25 plus 273. We may not need this, but I'll do it anyway. 298 K. So we know this is 298 K, and that's a negative term. And we know this one is negative. Well, we know, actually, what do we know about this one? If we're at equilibrium, that is 0. Delta G, 0 is negative, but this one is 0. So if this is negative times a negative, this is positive, then this one has to be negative. Correct? That temperature, this is negative, we proved that already, times a negative is positive. If this is 0, then that has to be negative. But in the same magnitude. When we don't know what the magnitude is, but it has to be equal in an opposite in sign in order to be 0. So what does that mean? That means this is exothermic. Exothermic. So what do we know about exothermic reactions? Go back to Le Chatelier. This exothermic reaction, where would we put the energy? Exothermic makes energy a product, correct? So we would have plus delta H. So if you raise the temperature, which way is this reaction going? Go back that way. Raise the temperature, you're reducing this, increasing that, so this one decreases. You get less of that, more of this. Okay, that's why the ratio decreases. All right. Let's see, I did a lot of bunny hopping in that one. Okay. Now, just to accept this. This is one of those equations that we don't have time to develop. But if you do know conditions, right? If it's not at equilibrium, and you want to know what the actual delta G for the reaction under those conditions is, and we know that if we calculate Q and compare it to K, we can determine whether the reaction will go forwards or backwards based on that comparison. Well, also if you use Q and it's not at equilibrium, then you can get an actual delta G relative to the temperature, the concentration, the equilibrium, the non-equilibrium calculation of Q, and that augments the delta G under standard conditions. Okay. Now that reaction, that equation can also be expressed in terms of changes in P. So if you have a reaction where all of the components are gases, and you calculate the P for that relative to the Q, then you can also determine the delta G. All right, and the R is 8.3145 joules per K mole, not the one that we use for purely gases that under atmospheres and liters volume. 8.3145 joules per K mole, rather than 0.08206 liter atmospheres per mole K. We use the one with the energy term in it. All right. So what are we trying to show here? This is straight out of your book, right? And the authors give a reasonably good explanation for it. What we're comparing here is processes that essentially go to completion versus those that reach an equilibrium state. So the ones that go to completion are like this ball rolling down. Goes from A to B, that's it. It's over, end of story. An example of that would be a phase change. Once the phase change is completed, you're down here at B. There's no equilibrium situation there. Whereas with a chemical reaction, you can go to one side or the other of the equilibrium position. The equilibrium is here in the middle, right? And your delta G states will be different here than here, but this will be the minimum. All right, so let's look at that in terms of what is that equilibrium point? Right, we're going to discuss this a little bit more, so hang on to those thoughts with the roly balls. So at equilibrium, there's no delta G delta G is 0. In other words, the delta G for the actual reaction conditions here, without the little 0, will be 0. In other words, there's no driving force under these conditions, under equilibrium conditions, for the reaction to go. Now that's as compared to the standard conditions. Under standard conditions, yeah, you will have some impetus either to go spontaneous or non-spontaneous. So what's the correction factor? Correction factor includes K, not Q. Why? Because K is an expression of equilibrium. Q is not. So if you know that K, if you're at equilibrium and you know it, then you substitute K here for Q, and now you're equal to 0 because delta G says there's no driving force. So delta G actual is 0. So you can set 0 equal to delta G plus RT log K. And now you can solve for delta G 0, put it on one side, minus RT log K on the other side. Now we have a relationship between delta G 0 and K. If you have calculated the K, or determined experimentally the K for a reaction, and you know what temperature that K is valid for, then you can calculate the standard conditions delta G. Or if you know delta G, you can calculate K, as long as you know the temperature. Because the temperature is a variable here also. All right. So let's look at this reaction. A gas yields B gas. And the only reason my double barbed arrow is that way is because I couldn't find one that looked like this. So I had to use that one. So what's the free energy of each gas, right? You can calculate the free energy. All you need, we're going to use the other equation now. So the individual free energies for each gas can be calculated in terms of their partial pressures. That's what that P stood for. I misled you. P is not equivalent to Q in the previous slides. P is partial pressure. Or it could be total pressure. If you want to know the G for the whole thing, you just put in the total pressure. So in this case, we're going to calculate the actual free energy for each of these gases, right? They're in the same container. And if you start from this side with 0 fraction of your A reacted, it's all A on this side right there, or on this side where it's all B on this side, and just let one or the other of them react, the A will decrease, of course, fraction of A will decrease, and the fraction of B will increase. Or if you go from this side, the fraction of B no, that's not right. I'm sorry, that's not right. This is only fraction of A. But you can imply, if the fraction of A is increasing, the fraction of B is increasing. A is decreasing, B is increasing. Or you could start from this side, right? If all of the A has been reacted, then you're going to have only B on this side. And you can reach equilibrium from that direction as well. So the equilibrium position is going to be somewhere in between, right here. In this case, it's 0.75 fraction of A. So we can calculate the free energies of each of these gases as the reaction proceeds. All we need to know is the partial pressure and the temperature. Oh, and the standard state delta G's for each one. So what's the total free energy for the reaction? Well, it's the sum of the two. So we're going to say as A disappears, the free energy of A decreases. Okay? Since the partial pressure of A is also decreasing. It just stands to reason from the equation. And similarly, as B appears, the free energy of B, the actual free energy of B, increases, since the partial pressure of B is also increasing. As long as the free energy of B is less than G of A, free energy of B is less than A, the reaction will proceed to the right. If it's the other way around, right, if the free energy of A is smaller than the free energy of B, then it's going to proceed to the left until they meet in the middle. In that case, now you've got a situation where the free energies are balanced and you're at equilibrium. Right? So what does that mean? That means that you subtract the reactants from the products and you get 0. Delta G at this point is equal to 0. You're at equilibrium. Okay, I don't know if that helped or hurt. We'll see. Let's look at this one. We've determined that if we're at equilibrium, then this equilibrium value here, inserted in the equation, will give us delta G under standard conditions. So let's look at remember when we were talking about equilibrium, when K equals 1 or K is greater than 1 or K is less than 1. If K is equal to 1, then we plug it in here. And the log of 1 is what? It doesn't matter what your base is. The log of 1 is always 0. Because e to what value is equal to 0, is equal to 1, e to 0 value is 1. Or if it's natural log, excuse me, that's natural. If it's common logs, base 10, then 10 to the 0 is 1. Right? So that doesn't matter what the log is. So what does that mean? That means if k equals 1, delta G0 is 0. Right? Under standard conditions, there is no free energy drive for this reaction. If k is greater than 1, plug that into your equation. If k is greater than 1, then the value is negative, right? Because the log of anything greater than 1 is going to be greater than 1 also, and the term then becomes negative. Delta G is negative, so if k is greater than 1, delta G is negative and the reaction is spontaneous. If k is less than 1, then this term becomes negative, and a negative times a negative is positive, and delta G is positive. So if k is less than 1, then the delta G says that that reaction is not spontaneous. Okay. So let's close it out with a discussion of, go back to Clausius' original objective, and along with Gibbs, and find out what's happening to that energy. Where is it going? Well, Clausius said that entropy is an explanation for why the energy is being lost. But Gibbs says this is an explanation for the maximum amount of useful work you can get from that reaction, even if you do lose some of it. This is the maximum. You cannot exceed this amount of useful work from any reaction. Now, under what conditions can we say this? Well, the Carnot and his son, Sadi Carnot, would say that for any process, well, first, let's put it in Gibbs terms. Delta G equals delta H minus T delta S. So Gibbs is saying that this is the potential, this is the loss, and this is what's available for work. So this would be equal to W max, right? So that's the most amount. But we know we're not going to get there. The only way that you can get that value is if the process is reversible. So if you go from one side to that side, then it has to be perfectly reversible along the exact same path. Right? And there are no natural processes that are reversible. They're all irreversible. Theoretically, though, this reversibility can be postulated as long as the changes are very, very, very small, infinitesimally small. And that goes back to concepts in calculus. So I'm not going to expect you to deal with it here mathematically, but conceptually, if we take very small steps, like almost immeasurable, one direction or the other, that would be a reversible process. And that would give you the maximum amount of work. But if we did that, say with a heat engine, just make small steps, right? One molecule reacting at a time, you'd never get where you were going with a heat engine, right? You need lots of energy released at once. So the irreversible process is practically what a heat engine is designed for. And this one is the maximum potential. So we're never going to reach 100% efficiency in our engines. Internal combustion, external combustion, doesn't matter. Any type of energy conversion, you're going to lose energy here first, and then you're going to lose energy here because the process is irreversible. Now, here's an expression. I know that's a lot to throw at you in one slide. Let's break it down. In fact, I think this is the Clausius-Clapeyron equation, or one form of the equation. I'll look that up and append it to the video. This expresses the temperature dependence of K. Right? And we know from previous calculations that if you say K is a certain value, then if you change the temperature, K will change. I think we have talked about this when we discussed equilibrium. So look at the form here. This log K, if we set that equal to minus delta H, and that should be superscripted 0. Somehow that messed up. Okay, there's another correction to be made. There and there. That should be H0. In other words, standard conditions. The normal enthalpy, and this is the normal entropy for the reaction. If you take this value and divide by R and multiply it by the inverse of the temperature, so we have to do this K calculation at different temperatures, then this term right here becomes the slope of the line. That's why it's negative slope, see? And the slope of that line, this value right here, minus 11,645 in this example, is equal to delta H 0 divided by R. So if we plot the log of K against the inverse of temperature, we get this equation. And we can calculate delta H from this equation. All we need to know is measure the slope and set the slope equal to this term right here. We can also tell what, delta S0 is. All we need is the y-intercept. The y-intercept is 24.924. Set that equal to delta S divided by R. And we know what R is, it's constant. So we can solve for delta S out of that. So all you have to do is run this experiment and determine the K for the experiment for each one of the temperatures. Plot the data, and you can get both delta H and delta S from it. All right. Summation statements. And we're good. We're a half hour. We got a half hour to go. Achieving the maximum work available from a spontaneous process can occur only by this hypothetical pathway. In other words, where it's reversible. In the real world, all of these processes are irreversible, and that means any real pathway wastes energy. You'll never get all of it back. All right, I thought this was funny. This is somebody's expression for the first law, where you can't create energy, you can't destroy energy, you can only change its form. So the first law expression in those terms is you can't win, right? You can't make something from nothing. You can only break even. In other words, you can't get more energy out of a system than you put in. All right, and then along comes the second law. You can't even break even, right? You can't break even because Entropy says that you're going to lose some in the process every time. Any transfer wastes energy. Unless you can transfer that energy to something at absolute zero. That's the only way you can get it all back. And that'll never happen because we cannot create a heat sink that is exactly absolute zero. Right? I may have shown you this before. Absolute zero is a hypothetical place. How do we measure heat transfer? No, better yet, how do we obtain low temperature? Well, you couple two systems together like that. This one's at low T and this one's at high T relative to the other one. And we want this one to decrease in temperature, right? We want temperature to go down, right? So that can happen as we transfer energy, heat, to the other side. This temperature drops, okay? This is known as the heat sink. So, how are you going to get to absolute zero? Are there any heat sinks that are lower than absolute zero? So that we can drop that one to K, 0K, right? To your heat sink over here? Never happened. You don't have a heat sink that's lower than absolute zero. So we're never going to reach absolute zero. Now, there are some scientists that claim they have, but they do it one molecule at a time. And their reasoning is that if the molecule is moving, actually they use atoms. Because if you use a molecule, then you've got bonds that you have to deal with. So throw out the bonds, use atoms. So they use atoms, preferably noble gases, so you don't get any reactions. And these atoms are moving. And they fire lasers at them. And they tune the laser exactly to reach. They tune the lasers exactly to reach the kinetic energy of the atom. And if they have enough energy, exactly right, the atom stops momentarily. That's absolute zero. So I guess technically you could reach it, but not in practical terms. Okay, and then the third law, you can't break even, you can't win, you can't break even, and you can't get out of the game. In other words, if I don't like this game, I can just leave. I can pack up my marbles and walk away. Nope. Third law says you can't even do that because you can never achieve absolute zero. So that's the last slide, I think. Oh, the takeaway from all of this is anytime you use energy, you degrade it. In other words, you increase the entropy, so now it's less useful. So in chemical systems where you can handle large evolution or large exothermic or large endothermic changes, you can do this very quickly in single or 2 or 3 steps. But in living systems, you can't afford to extract energy from a process in one big step, right? If you do that, you ever seen a spoon of sugar and somebody takes a lighter, cigarette lighter, and catches the sugar on fire, it'll burn. If you did that in your body, you would incinerate your body, right? Too much energy, too fast. So what the natural systems do is we do it in steps, right? We degrade that energy level stepwise, little at a time, and extract useful work as you go. So what that tells me is that this slow step process of extracting energy from combustion is more efficient, right? Because what do we say? Small steps bring you closer to delta G, closer to maximum work. So if you make small steps, living systems are not stupid, right? If you do these things in small steps, you can get more energy from it. Okay, so that's all I have to say about that. We're done there. And that, that's the best job I can do at explaining entropy and spontaneous reactions. Next week, we'll look at the review document. And there are some problems in there that I hope I've given you enough information to do. But if not, if you feel like you're stumped, go to the review document, worked problems, and see if the worked problems make any more sense. And then come back on next Monday, and we'll take the review document, we'll go through it, I'll pick out some things that are of substance and not repetitive, and we'll work those problems. And that's really, in the long run, that's the only way to learn chemistry, is work problems.
Hey, Dr. Bly.
Yeah, sure.
We're not going to have a final, are we? 'Cause I'm just wondering. I didn't see it on the syllabus.
Oh, well, let me check to be sure if we're on the same. No, we don't have enough time. So what we're going to do is we'll have an exam on the 3rd of May at the latest for this topic. And then on that day, I'll introduce electrochemistry. The problem with that is there's not enough time to do a review for electrochemistry before the exam. The exam on electrochemistry will be during finals week. So what I've got is a review that's already recorded from a previous semester. And I'm going to take another look at that review and see if it's still good enough quality. And if not, what I'll do is I'll just do another recording of a review and post it instead. So I have to decide if the existing review is good enough quality, even if it covers the topic sufficiently. But in the earlier days, my video quality wasn't as good as it is now. So I'll check it and be sure that that the quality of the video is not a stumbling block. And then if necessary, I'll just re-record that video and make it available as soon as possible after we introduce the materials on electrochemistry. Okay. Yeah, that was the long way to answer your question. No, there's no final.
All right. Thank you.
All right. I guess that's it for today. If you had no questions, and